I'd like to start off by giving a brief introduction about our project. Currently, the ISS has a life support system that provides oxygen to the astronauts. However, only 50% of that oxygen is actually being recovered into the system. Resupply missions are too costly and not fit for long-term travel. So our customer, Honeywell, has been tasked with coming up with a solution. They're doing so by closing the loop on the system and raising that percentage up to 100%. This is done by taking the cabin air and through a series of reactors, converting them into useful products like water. The section we'll be focusing on involves methane pyrolysis, which is an endothermic reaction that's going to be splitting the methane into its core components of carbon and hydrogen. Currently, a lot of our focuses are going to be on size, power consumption, heat loss, and cooling, which are the main concerns when developing this new system. This leads us to our project goal.
Now to dive into the problem description. So like Abe was saying, a methane pyrolysis reactor generates a lot of heat, which can be less than ideal when you're working in a space-based platform. So the goal of our project is to design a system that regulates this heat through thermal management. The main thermal management approaches we used were insulation, material treatment, and a recuperative heat exchanger. The main evaluation criterion for our design will be its equivalent system mass, or ESM. ESM is a factor that takes into account the pressurized volume, unpressurized volume, and power requirements of the system, and translates them into a single mass value. The lower this ESM value, the more optimized the system solution will be.
So a little bit of background on our system requirements. So our project is kind of interesting because we had to rescope our project back in November. Because of this rescope, we had to redo all of our system requirements to match our rescope project. But a lot of these new system requirements are based on the old system requirements, but they were just tailored to match what we were making, so our tool. After our team reviewed all of the documentation that our customer has sent us regarding the project and what they kind of voided during the rescope, we looked through it again and we made sure that all of the needs that the customer wanted is in our system requirements. So one thing to see here is our major aspect of our tool is using the equivalent system mass to optimize the system itself and to give us an output of the optimal material that the customer, given their constraints that you can input in our tool, will have. This system requirement is saying the model shall calculate NASA's equivalent system mass for the total system consisting of the inlet, outlet, heat exchanger, reactor shielding, and system housing of the methane pyrolysis reactor by summing the system mass with the system volume and system power after being converted into their equivalent masses. So this right here is basically the summation of our tool and our customers' needs.
When we first began to approach the problem, our team focused on finding a general system design. We were given lots of creative control with the 3D structure of the system, so we considered several variations of system components that could be included to maximize thermal efficiency while also minimizing the system's total ESM value. The left design showcases a standard heat exchanger model where we'd hope to yield a perfect thermal efficiency by utilizing the higher temperatures at the outlet of the reactor to preheat the cooler temperatures at the inlet of the reactor, with any heat loss being prevented through insulation. The middle design assumes that there's excess heat in the heat exchanger model, so active cooling is included at the reactor outlet to ensure that the temperatures are being decreased to the specified 150 degrees. And finally, on the right is one of our earliest concepts, which attempts to utilize several mini reactors rather than a singular reactor to complete the methane pyrolysis process, the theory being that it's easier to heat a smaller volume. After compiling the pros and cons for each of the potential designs shown on the prior slide, a trade analysis was performed where various trade factors, such as power usage and thermal efficiency, were considered to decide with the final design that would be modeled within our tool. Each trade factor was given a weight from 1 to 5, with higher values indicating higher importance. From there, each unique design was given a score for the particular trade factors that also range from 1 to 5, with higher values indicating higher risk. Finally, by summing the weighted trade factor values for each design and then comparing their respective scores against each other, our team was easily able to determine the heat exchanger model as a preferred design choice that we would base our tool off of. Looking at the heat exchanger model, our team determined it would have the best performance in both power usage and thermal efficiency, since only utilizing a singular heat exchanger would minimize the risk of needing excess power, as well as the number of components experiencing real-world inefficiencies and needing insulation. In fact, when compared to our other designs, the the heat exchanger model had a minimized risk score for the entirety of the project, but also for each individualized trade factor. Therefore, our team ultimately decided to utilize the heat exchanger model above due to its ability to increase thermal efficiency and decrease the amount of power required, with any inefficiencies being minimized through the use of heat shields and insulation. With the chosen heat exchanger model, our team was then able to code several functions covering each of the system components, such as the insulation and inlet-outlet piping, in addition to making the tool user-friendly with customizable configurations and a GUI interface.
For the ESM optimization portion of our code, the user first defines the properties going into the code. Once this is done, we run through our inlet function, our reactor function, our heat exchanger function, and outlet function. Since our insulation function depends on other component properties, the code will then iterate through the inlet and outlet matrices, the insulation thickness, and both the heat shields and insulation's materials. Within this, the insulation's function is called. Then the heat loss and ESM total are calculated and input into a matrix, which saves the properties and configurations of all the components for that particular ESM calculation. After that is complete, the optimization function will find the lowest ESM and output it.
What results from our optimization tool is a multi-tabbed GUI that allows the user to input data for the system. What results is of course the best ESM along with its components. One thing to note is that the ESM that we calculated is only one of many possibilities that are valid and meet the system requirements. This means that the system can actually calculate a better ESM provided it's given the right input. And as a final note, one feature to notice is the ability to download the materials and the results to make testing and analysis in the future easier for the user.
Here we have the surprises, lessons learned, and problems overcome. We learned that we must have a clearly defined project scope because scope creep is real, and we ended up having to shift directions and take on less and take on more in different areas throughout the project. Also because concrete system requirements are important so that we can follow a consistent process throughout the entire project. It's also very important to manage our time correctly, especially within group work, because it's important to balance the work evenly amongst each individual on the team.
Once everything is finalized, the following deliverables will be delivered to our sponsor. First, we have our MATLAB programming tool, which will be delivered in the form of a MATLAB application file. Then we have our CAD design, which will be delivered as multiple SolidWorks parts and an assembly file, along with the drawing files as PDFs. Lastly, we have our final report, which will contain our software design document, our literature review, and our technical data package. All deliverables will be capable of email delivery or through the use of online file sharing services.
We would like to take this time to thank our sponsors Amanda and Kevin, as well as our mentor Heather, along with 3 professors that helped us through this project to get it to where it is today.
And that concludes our Design Day video. On behalf of the team, thank you for watching and stay safe.